add to the picture a little bit. First of all, let's go even deeper along this treacherous direction to what fellow colleagues that are not necessarily fundamental physics interested want to package their own name around and call it chemistry. But understand that the central science, every significant nugget of knowledge learned in chemistry, from the structure of the atom on, was established by a physicist, not by a chemist. So, just so you know that, chemists are the engineers of chemical systems. Nothing bad about that, but chemistry's not its special science any more than engineering is. It's just an important application and usage of those tools. It's important. Things driving nuts. Okay, so we got a proton, and we got it interacting with this electron. Now, we know two things. It's an attractive force, so it's going to pull it to the center, which would imply maybe that they would collide if they happened to be aligning in a certain direction. We know something else, too. Under some conditions, at approximately this diameter, they seem to hold themselves in place. How might you maintain a particular distance of separation between a positive charge and a negative charge? If the distance of separation is constant, it implies the magnitude of the force between the charges is also constant. If it's not constant, the distance is not going to be constant, the separation. How might that possibly arrange itself in nature? You think of at least one possibility how that might occur in a very obvious way that we've thought about without even looking at it. Cricket? Cricket?
Does that have anything to do with the motion?
Well, if the electron were moving, well, now, if gravity can't apply, if we're so out of the range of this, well, I'll tell you what, electrons are called leptons on a fundamental physics taxonomy level. So they're not hadrons, they're not nucleons. They don't interact by strong force. So it doesn't matter anyway. So you've got these things attracting, but somehow they stay together with approximately the same distance of separation without ever colliding, staying stable for, in some cases, billions of years. They must be subject to the same electrical force interaction. How might that happen? It does require motion. You need motion. Without motion, it won't work. Because if that's there at rest, that's there, the net force is going to basically pull it right into the center. You're going to have annihilation. But it doesn't happen as often. Well, practical purposes, not really. Something else happens. Before we even get to that, got an electron, it's subject to this force. What's the acceleration of this electron? Simple question, F equals ma. How much, as this electron is subject to this force, and it's the only force there by this proton, what is the acceleration of this little fellow? Take that number, this is F, divided by m, that's going to give you your acceleration. So let's just calculate, and for your notes, let's just add the next question to the problem. I'm going to put it over here. Yeah, I'm going to put it over here. I want that part before. So, question 4. What is the acceleration of Q2? And this is assuming it's just in isolation with Q1 and nothing else going on here.
Are we going to make an assumption in uniform motion around that?
We're not going to make an assumption. We're going to come to the conclusion that that's the only case that makes sense if these are point particles. There's nothing else that will allow that to happen without the diameter effectively changing significantly.
The acceleration I got was essentially 1 times 10 to the 29.
So the net force is m times a. So a would be the net force divided by M2, which would be negative 9.23 times 10 to the negative 8 newtons in the I direction, divided by 9.11 times 10 to the negative 31 kilograms. So that's about 1 point something, negative 1.2, negative 1.1.
Zero.
Zero.
Yeah.
Overestimated again. And 31 minus 8, so 23
23.
meters per second in the I direction. Wouldn't take you very long to get to that nucleus.
It's gonna get faster as it gets closer too.
So think about G. This is 22 orders of magnitude larger than G. This is a G whiz.
We're gonna measure its angular speed.
We certainly could, absolutely. Imagine where I might go with this. Huh? Okay, so the consequence of this is that it's going to accelerate. But it's going to accelerate while maintaining the same distance of separation, therefore the same electric force of the interaction. If it doesn't, then we don't have the simple model of the atom that we otherwise would infer. So the only way this could happen would be if the motion of this charge is a circular pathway, or a circular path, or route, if you will, along or around the central proton, or the central M1, if you will. And as it moves, to maintain the same separation distance, means that the acceleration toward the center, wherever this guy is going, so if it's down here, its acceleration and its net force is going to be directed here. As it keeps going, wherever else it is, the same distance of separation, therefore, and you've still got the force of attraction. Doesn't matter how fast it's going, Q times Q over R squared is going to be how, and times K is going to be how you describe the attraction. So wherever you are, maintain that same separation distance will maintain the same electric force. And that will be established. Well, at least the only motion that you can include is that it would have to be a form of uniform circular motion. Because if there were any acceleration that changed the velocity, or I'm sorry, changed the speed of Q2, it would not maintain the separation distance. And once it didn't, it might in fact lose orbit altogether. Or the orbit would be some crazy thing like that rock of ice that shows up anywhere observable near the sun every 100,000 years or whatever. They found that, you know, about that little dwarf, it's not even a dwarf planet, it's just some big rock that has this ridiculous orbit around the sun.
So is that the orbital acceleration, or is that towards
It's
the
the
center?
net acceleration, but in order for the separation distance to stay constant without the disturbance of another force, this is just one, if you will, hydrogen atom out in the middle of nowhere, not even close enough to another hydrogen atom to form H2. It's just sitting out there, it's still stable. We know it because we measured it, we observed it in these hydrogen clouds that are very low density out in the middle of nowhere. So we know it can happen. If it does happen, it requires that the acceleration be radial or centrifugal. So to answer the question, yes, it is, but I just want to give a justification for why, rather than just telling you it is and believing. Okay. So the implication of this, the only way it can happen and maintain this separation distance, if all the acceleration is at a 90-degree angle to the velocity or the motion. If it's not, you're going to accelerate outward and this orbit's going to change. That's the only way it can happen. Turns out it's not quite realistic anyway. That's why the Bohr model of the atom broke down very quickly as soon as you apply it to anything but a hydrogen atom. But it works very elegantly for a simple one electron, one proton system. So where are we at here? Let's go to step 5. Because I'm writing all over in between the lines here. So what is the speed of this electron? What does it need to be for Q2 to maintain constant R and ultimately FE? Well, this has to be centripetal motion. So the implication of this is that it is in fact uniform circular motion. Any other type of motion will not maintain this particular requirement without throwing waves or something that's completely different from our normal mechanical sort of interpretation of the universe. So to this end then, what we can say is that the net force, I'm going to use magnitudes now, well, I could even write it as a direction, as a vector, will be related to the electric force, and the value will be what we call the centripetal force, mv squared over r, pointing along the direction of, I'm going to call it r, of the center of this guy outward to wherever this one is. Wherever it's located, it's always the interaction, the r vector is always from here to here, from here to here, from here to there. But because it's going to be the same value everywhere, r will change at all points. But the magnitude of this will correspond to the magnitude of this over here. So what we're left with is Fe, the magnitude, should in fact be related to mv squared over r. And we will derive from here, already know what that number is, and calculate that. About 9.23 times 10 to the negative 8 newtons. Therefore, the speed should correspond to Fe times r. Divided by m, we get the square root of that.
Looks like about 7.4 billion meters per second.
I'd say it's kind of fast. Because you're taking 10 to the negative 8, and you're multiplying it by a pretty crazy number, 10 to the negative 11. So now you're at like negative 19. But then you're dividing it by 10 to the negative 31. So now you're at like 10 to the 10th or something. And then you take the square root, you're out 10 to the 5th, 10 to the 6th or something there. So we plug the numbers in here. We've got 9.23, that's 10 to the negative 8, times 5 times 10 to the negative 11, and we divide all of that by 9.11 times 10, negative 31 kilograms. Take the square root of that, and the negative 19, so 31 minus 19 is 12, 13, 12, 13, something like that. 31, 19, 12. There we go. I'll do the arithmetic. So it's 10 to the 12, you take the square root, it's gonna be about 10 to the 6th, whatever the little numbers are. So 5 times
Yeah.
10, 3 times 10 to the 6th, 2 times?
2.25 times 10 to the 6th.
So 2.25 times 10 to the 6th meters per second. Yeah, it's kind of quick. Now, lest that number on the surface be disturbing or problematic, just understand that really, we're only talking about 2,000 kilometers per second. It's really not that fast, right? 2 kilometers. Or, if you will, 6 million miles per hour or so, 5 million miles per
What do you
hour.
think about,
What was the diameter of that?
exactly, if you think about the circumference of its path.
From the time it's on one side to the time it's on the other, it's almost instantaneous. It's coming back to the same
Well,
point.
Yeah, it's going around so fast, for all intents and purposes, it's solid.
It's a fan that you can't see through because the blades look like they
Yeah,
form a
you can't
shield.
push through, you can't, it's,
Kind of makes sense now that you couldn't peek in through and sneak past the electron to get to the nucleus very readily. It's going to make some sense. And now, is it kind of like a marble? Well, now it kind of makes, yeah, it kind of seems like that might work in principle.
when you have multiple of these things whizzing around, what's preventing them from colliding? Their own propulsive.
That's where the model breaks down.
Yeah.
Now, and it breaks down, and hopefully we'll get to that last example here in a moment. It does break down because they could never collide because of their force of repulsion.
Right.
But they would always have to be oriented in such a way that they don't repulse so much that they push each other off. Now, the funny thing is that model broke down. I've never done the analysis, so I'm just sort of speculating. But this analysis and the limitations of this little model predated the interpretation of an electron having spin. Okay, when the electrons, think of it as being these little tops that are moving real fast, because they're spinning, they have a magnetic field. Because they have a magnetic field, if they're pointing in opposite directions, they also will attract, not repel. Which is why we say that electrons have up and down spin, because with respect to each other, if they don't have opposite spin, they won't stay together. And so if an electron and another electron share the same orbit, they have to, by their own necessity, have opposite spin, so they're like positive and north-south magnets attracting, 2-bar magnets. Now that being said, I've never extended this model to account for what we understand experimentally in terms of how this magnetic moment and these magnetic values are in the atom. And it's a reasonable analysis. I mean, would that help account for things that would not require quantum mechanics per se? I doubt it. There's other limitations, I'm sure. But it makes you think. So there are ways you can fit 2 electrons even though they would otherwise repel. And they would just have to always maintain a separation from each other at all times. Okay? Now, but the other thing I want to point out is lest that number be troublesome. I was kind of joking around about the 2,000 kilometers per second. That's kind of fast. The speed of light, this is like 1% of the speed of light. So we think in terms of the big picture, what is necessary in nature and what's allowed. This is so slow compared to what nature will allow anyway, that it's not an unrealistic possibility. If that makes sense. Right? The speed of light is about 3 times 10 to the 8th. So this is 1% of nature's speed limit. So, you know, it does sit inside the box pretty nicely. If that number came out to like 3 times 10 to the 8th or 9th or something, then you'd know this is just full of it. But the fact that it does sit so well below that speed of light threshold is kind of comforting. I find it. I'm sensitive guy. Now, one other thing before we move on to my next example, next application. We got speed, we got mass, we got kinetic energy. So how much energy of motion does this electron have while it's in there? 1/2 mv squared. So we're going to add one more last picture to the puzzle for just this analysis. Let's just look at the kinetic energy. Kinetic energy tells us even more stuff that are interesting. This is just taking one step to the next, just using Newton as our guide. We're not even going any farther than that. This is 17th century physics. So what is K? Well, to calculate K, I gotta keep erasing all this stuff. Now, by the way, there's two ways to calculate K in this particular problem, which are worth noting. First of all, the standard approach is to say that K is equal to 1/2 mv squared. We know V, we just calculated that. Heck, we could backtrack in our calculator and remove the square root, right? Because we had to do a square root to get V, so we just step back to the previous entry, delete the square root function out of it. That'll give us our V squared multiplied by M. Or we could just say FE times R. Same thing, right? MV squared corresponds to FE times R in this particular case. Not always, but in this particular case. That's kind of cool. So, for me, the easiest way to calculate it would just be to take 9.23 times 10 to, put a little brackets on there, times 10 to the negative 8 newtons, multiply that by 5 times 10 to the negative 11 newtons. Unfortunately, that'll give us newtons times meters. There's your joule. So we're all golden. We got joules. Long majority. I'm sorry, this is really, really bad jokes today. But at least they're G-rated, that's the good. So what, it's like 4.7 times 10 to the negative 19. 18, I'm sorry, 18. Yeah, because you get 45, so about 4 I'm pretty sure it's about 4.74.
You're missing the 1/2.
1.61 is what I've got, but.
Oh, 1/2, I gotta put a 2 in there, thank you. Then it probably comes in. What does that come out to then, right? Oh, no, I gotta put the half here, thank you, sorry.
Yeah, I got 2.3 times 10 to the negative 18.
So we can use FER over M or is that just kind of
I totally am full of it, by the way. That's supposed to be a 2. I don't know why I keep going. Every possible way I can screw up the wrong number and put it in there. Damn. Like, how many ways can I go home and have
for a second.
and run out of gas? Well, I'm going to find every single one. I don't want to just get there. I want to make sure I make my trip long enough so that I don't. Divide this by 2. Jeez. Okay, let's I do want to work out. So, okay. Not obviously. Okay, so there we go. Okay, we've got the energy. Now this number seems tiny. Yeah? Let's think very carefully about this. We've done these things a lot in thermodynamics where we estimated the energy of a gas particle sitting in a balloon, for instance. How much energy would an atom have? Hydrogen, it doesn't even matter what it is. Would a gas particle have sitting in a balloon at room temperature? Remember how we calculate that? No? Yes? No? See, this is why I wanted to do that thermodynamic problem the other day. So, I think it's very important to remember that you can always integrate ideas for basis of comparison. Otherwise, this number means crap. It means nothing. But when you start seeing how it relates, hopefully you can start finding some things. Internal energy of a gas system. Okay? If you take a gas system at some temperature, say temperature in Kelvin I'll use, 300, just to keep the number kind of round. Let's call it 300 Kelvin. A little bit warmer than room temperature. internal energy of one atom, or one gas particle. As these things are bouncing around at a certain pressure, a certain volume, et cetera, et cetera, et cetera, the internal energy of one atom this can move, and let's make it monotonic, atomic, so we don't have to deal with 3 halves. So let's use 3 halves, okay? This will be about 3 halves times the Boltzmann, K with a B now, not a C, constant, times the temperature in Kelvin. So that's about 3 halves times Boltzmann constant. Remember this number? That's the gas constant.
1.38 times 10 to the 1/3.
You know, it drives me nuts when physicists all of a sudden start using gas constants and numbers that aren't SI, after berating you for the first part of 211, saying, if you're not using SI units, you're somehow an illiterate, and, you know, we use English units, and blah, 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 all the other crap that people try to tell you to stand on their little soapbox. If we're going to go that route, let's use the fundamental quantities. Also, the gas constant is per mole. We're not talking per mole, I just want to know per atom. So there's a lot of different reasons for this, but so it's joules per Kelvin. If we multiply this by Avogadro's number, it would be joules per Kelvin per mole. Okay? And we multiply this by 300 Kelvin. So lest us worry about that number being too small, if we look at what the average energy of just an atom floating around in this, what is this? This is about 2.8, half again, or one more, 4.2, 1.5 times 4.2, so 6 times 10 to the negative 21.
6.2 times 10 to the negative 21.
That was kind of in the ballpark. Joules. That would be the energy of one gas particle, okay? This energy is large. This energy is not small. The kinetic energy of the electron moving around inside the atom is significantly larger than the kinetic energy of a randomly bouncing around gas particle in a balloon. See how the picture sort of fills in? This is what an atom would have, just a typical old atom. Joe Schmo, nothing special. This would be the energy of its electron inside it, much higher. So if anything, this is a large number, not a small number on that scale. Yes, sir?
Well, I guess I'm confused, if the electron is part of the atom, why is there a larger number within the atom, and then the atom as a whole have a smaller number?
For the same reason that you can have a full gas tank with your car not moving. You can have all this energy inside built up, but that's not the energy of the whole system moving around. That's why it's internal and not systemic kinetic energy. Great question.
But there is a separation there. It's not like when we went over, the sausage rolling down the ramp, and part of the energy goes into
Long story
rotation.
with the sausage, by the way.
But, right, when something's rolling, part of its energy goes to rotation, part of it goes to translation, but it's
Yes.
not the case here. There's a separation between
Correct.
the two things there.
And the reason for that is the chicken is a sphere, so to speak. When we look at the atom as a system, when we look at this guy, we're taking one particle and saying, okay, it is, there it is, it's just sitting there, or it's moving around. Now we look inside of here, and you've got something that's doing this inside. But that's distinct from what this system itself is doing as it's moving around.
Yeah, just like if we treat my eraser as a particle and I throw it at you and we calculate its energy, we're not talking about the temperature inside of it and all that kind of stuff.
Yeah, it's a distinction between a thermal system and just looking at the mechanical aspects of the system. Now, again, point of illumination. The energy of the electron inside the particle is orders of magnitude larger than the mechanical energy of the particle itself. Does that make sense, or does that seem like that should be the case or not? Can you rationalize, can you think about it? Ask yourself this for a second. Talk about it. I mean, just brainstorm.
Makes sense.
Brainstorming, because I want to give you another sense of perspective, because it all fits together in our world if you really think about it. Okay, thank you for the quorum and thinking about it and bouncing ideas off your neighbors. Cool. So, gasoline, you burn it. TNT, trinitrocellulose, whatever, blah, blah, blah. I forgot what it is. Nitrotoluene. If you can tap into that chemical energy, you can take a system that has very apparent motion by its temperature and whammo, make it just explode, pardon the pun, right? Why? Because there's all this untapped energy, which is chemical energy, is always about the electrons. The electrons always about electrostatic electro-interaction. It's all inside, you're just tapping it out. Right? Popping open the keg and filling up the mugs. You're expanding that, you're getting it out, but it's in there until. So you don't really notice it, it's just gas particles bouncing around. But you take that little spark, if these little particles happen to be hydrogen and there happens to be some oxygen around, you get an exploding blimp over some stadium in 1920. Right? That's the Hindenburg. There's all kinds of energy, you can tap into it. And then it's even worse when you look in the nucleus. You can even get more out of it. Here's an interesting fact. It takes dynamite to detonate a nuclear atomic bomb, atomic explosion. Isn't that wild? You have to use the chemical energy to get enough compression to get the damn thing to do its thing. And to get a thermonuclear process, a fusion reaction to happen, at least on a exploding scale, you got to detonate an atomic bomb in order to get that to happen, in order to get enough energy to cram that shit together. Then you can pop it out. Everything's in order, it's a scale. Everything is about a scale of things. You start seeing how this stuff fits in. It's an amazing collage. Awesome application. So, but that's the energy inside. Now, most of you had chemistry, haven't you? I know not everybody has, but most of you have. What typically, when you guys are studying the atom and studying, I'm not talking about mole chemical reactions, but we're looking at like electron transitions. What units did you often, do you know what, besides a joule or a calorie, do you remember what, there's another unit that gets used oftentimes when looking at like electron energies? Because these numbers are too horrible to look at, right? 10 to the negative 18.
There's +1 and -1.
Actually, I don't know. The electron volt. There's another form of energy called the electron volt. And what's an electron volt? Well, in short,